Hello, and welcome to the Group 6 final demo video for the Battlefield Effects Simulator robot sponsored by PEO SHRI. This demo video will include a brief project overview and the motivation behind this project, the goals and objectives for this robot, a description of how the robot runs via our use case diagram, and finally, a full demonstration with the explanation of the product.
The Battlefield Effects Simulator robot is a small-scale version of the robotic system that will be utilized on live fire ranges to support training, realism, and feed threat representation of pyrotechnics. This version of the robot will maneuver through rough terrain to a desired location accurately and fire pyrotechnics when proper safety signals are met. The BES for the prototype will not be on top of the robot, but will still be in communication with it. The robot will interact with the BES to send the safety conditions for when it is clear to fire the pyrotechnics. The safety conditions include that it is in the correct location and that it is plus or minus 10 degrees level.
Our team has also had the opportunity to attend ITSIC, the world's largest modeling, simulation, and training event this past Monday and Tuesday to brief Army leadership, including the PEO, who is equivalent to a 2-star general, the DPEO, PEO SHRI Chief Engineers, the UCF Board of Trustees, the Ensign National Director of the Pentagon, and other leadership. This has been such a great experience for us as students who are preparing to enter the workforce. We've received great feedback from all we presented to, and they're looking forward to the future of this project. Our motivation for this project comes from the government's derived need for a modular open system robotic platform that aligns with the Robot Operating System military framework and ecosystem. This robot is intended to increase training realism and feedback and improve safety measures during training by removing the human element when it comes to pyrotechnic handling. The overall takeaway from our team to our sponsors at PEO SHRI is that this product will provide a rapid prototype and technical data package that can be leveraged by the Army to increase training throughput, improve safety, and reduce cost of live fire training. The main goal for this robotic system is for it to be utilized on live fire ranges to support training realism and feedback, threat representation, and pyrotechnic handling. Our objectives consist of the following. The robot will use LiDAR data to create a map of its environment. It will correctly navigate to its specified destination. The robot will detect obstacles in its path and navigate around them. The robot will ensure it is level plus or minus 10 degrees when it has arrived at its specified destination. It will ensure it has arrived at the correct destination. The robot will send signals to the GUI via the ESP32 that it is safe to fire, and the GUI will send signals to the BES to fire pyrotechnics.
Now let's take a look at the use case diagram. As you can see, the user starts on the bottom left. It can tell the robot where to travel, or if the conditions are already met, it can skip on to firing the BES. If it tells the robot to travel to a specific site, it calculates the optimal route, sends the coordinates to the tablet, and then it checks if the coordinates match. If no, it will travel to the site. It will check if an obstacle is in the way. It will update the map with obstacles if there is an obstacle in the way, and then it will calculate the optimal route once again. Once it goes to do coordinates match and it says yes, it will check if the robot is level to the ground, plus or minus 10 degrees. If no, it will alert the tablet and tell it that it is unsafe to fire. If yes, the conditions are met, it is in the location that it is set to, and it is level, and therefore the BES will be able to fire.
We wanted to deliver as polished of a product as possible to our sponsors. Here in these videos, you will see the robot with all of its internal components exposed. This is the final product we delivered to our sponsors. In order for the robot to accurately navigate to its specified location, it must first create a map of its environment. This is done by first uploading the code that allows the robot to move and sends velocity commands through the Arduino IDE to the PCB. This can be seen here. Next, I spin up all the launch files necessary to create the map. This includes ROS core, the odometry files, the RP LiDAR file, and RViz. Soon, RViz, which is a ROS visualization software that enables you to see the robot's perception of the environment it's in, will pop up. This can be seen here. Because I'm using the raw SLAM package, the robot knows to take in data from the LiDAR. This initial map that is shown here is created from the LiDAR data the robot has gathered by just sitting still. As the robot begins to move, the map will continue to grow. The next clip will show the map growing as the robot is continuing to move around in its environment. When the mapping process is finished, we will save the map. From there, the robot is ready to connect to the GUI to receive the location it will travel to.
All right, so here's an example of how to use the GUI. So the first thing you want to do is connect to the robot, and then if it's successful, then you'll see that the status gets updated here. And then if we look in the console, you can see that it says that it's successful here, and then now it's also sending the coordinates of the robot and also the status of the BES if it's safe to fire. So this is the X coordinate and this is the Y coordinate, and then the 0 right here means that it's not safe to fire. So and that's why it's red right here. If it was safe to fire, then it would be a 1. So I'll demonstrate how it ends up being safe to fire. So if we travel to site A, for example, that's going to send that byte to the ESP, and now it's going to tell the robot to start moving. So you can see that it's updating on the map the coordinates, and then eventually when it gets to site A, we look back, you can see that it's ready to launch now. And then also in the console, you can see that it starts showing up as a 1 now, because that means that is now safe to fire, so that's why it's green. Okay, now I'm going to give an in-depth look at how exactly the communication works. So this is the ESP32 console, and then here's the GUI. So when we connect, it's going to be, we see that's true, so it's going to, now they're both connecting. So when we press like travel, if we want to travel to a site, it's going to send it to here, and then you can see it shows up as B. So it'll either be A, B, or C, and it sends 1 byte. And then if you press stop, it clears it here, and it's going to send a 0. And then that indicates we'll send that to Ross and basically say stop traveling. And then another thing that I focused on was I wanted to make sure that it gracefully disconnects in like multiple cases, like in case the GUI loses connection or in case the robot loses connection. So if I disconnect here, then you can see that this, since the ESP is the server, it's gonna be ready to connect again. So so like if you want to reconnect, it's gonna work. And then you can see that if we travel again, it's gonna show up. And then the other thing is if the ESP disconnects, so I'll do that, I'll disconnect it. Basically how it works is the GUI has like a timer. So if it doesn't receive a response, because this is sending the coordinates, so if it doesn't receive a response in 5 seconds, then it's going to disconnect. So you can see right here, connection status is false. So now they're both able to gracefully disconnect. So that's important.
Now here's a demo of us using the GUI in real time our team created that was uploaded to the government tracer tablet. First, we need to connect to the robot by selecting the button. As we do that, you can see the connection status change from false to true. When we go over into the console, you can see it was attempting to connect, and now it has connected successfully to our robot. When we switch over to the map, you can see that the blue dot indicates where the robot is. Next, we can select a site for the robot to travel to. As you can see, the GUI automatically calculates the most optimal route to the destination, and that destination pops up on our screen. On our GUI, we had selected Site A for the robot to travel to. This video shows the robot traveling to that site. The top screen shows the LiDAR data being used to navigate any obstacles. As you can see here, the robot detects the cone and moves around it to avoid hitting it. Once the robot has arrived at its specified location, it will ensure it's in the right location via our GPS through the GUI, and then it will ensure it is level plus or minus 10 degrees using the IMU. That data displayed is shown here in the terminal. Once the safety checks have been performed and indicate that it is safe to launch the BESS, our GUI will switch to ready to launch as well and allow access to the BES firing commands. Here we are setting the values for the BES to fire. Now, the BES will receive signal to fire its pyrotechnics. In this video, the beeps will represent the pyrotechnics firing. These next two videos are also examples of a BES being used in a live fire training environment. These BESs are stationary. Eventually, a larger scale version of our robot will allow for the BES to sit on top of it and be transported to and from specified locations like we showed you in this video. Thank you for watching our final demo video, and we look forward to answering any questions you may have in our final Zoom session.